Well, hi, good morning. Thank you for joining me in my shop. Today is March 10th, and oh my gosh, there's snow on the ground outside. How did that happen? I thought we were halfway to summer here and skipping right through spring, but nope, we're back. We're back to a bit of winter. It's just a dusting of snow, though. It's not very much at all. So what are we going to do with this radio now that it's in a condition where it's operating? I think I'm going to just start plugging my way through the old capacitors that are in here. I just want to flip this up. Took a few minutes to dust off these tubes a little bit and just to get the bulk of the dirt off. Oh my gosh, these were the dirtiest tubes I've ever encountered. Oddly enough, I think they've never been cleaned. It is really crusty on them. I was really quite surprised. So, okay. Dirt on the outside of the tube might cause the tube to run a little bit hotter, maybe, because it can't throw the heat off quite as well. So, what do we got going here? So I've left these guys in for now, along with their brother here. So these are the filter capacitors and the bypass capacitor for the output tube. I think we should start kind of with the output tube and the audio circuits. And the first thing we want to take a look at is what is the bias on the output tube, and what is the output tube? And I can't remember offhand, so I'm going to take a peek at the schematic here, and we're just going to bear with me a moment while I do my best to call it up. Here it is, and it's a 6F6, a very common output tube for radios like this. So 6F6, and it had a cathode resistor. So we're actually going to read the voltage drop across the cathode resistor, and the cathode is pin number 8. So that's this tube. Just make sure I got the right tube here. Oh, this is the rectifier tube. This is the output tube here. 6F6 output tube. So notice the glass bulb is bigger on this tube than these ones. These are bigger than later tubes that came, but you can see this is quite a bit bigger than this one. But this one's a similar size. Big tube, a big tube. Why? These tubes get hot. Inside them the heaters run hot. They produce a lot of heat. And why? Because these tubes have to conduct a lot, the rectifier tube and the output tube. They do a lot of work, and consequently they dissipate a fair bit of heat, so they're bigger. That's the reason. Okay, so we want to find the grid connection for this tube. It's kind of buried in behind here. One of those pins is the grid. It was pin 8, wasn't it? 8 was the cathode. And we want to measure the cathode to ground voltage because that represents the bias. So the cathode's going to be pin number 8. Then after I do the test, I will then change some capacitors here, and we'll repeat the test and see what difference it made, if it made any difference. So I got to spot the key. Luckily, there it is. The key is the part of the tube base that forces you to plug it in only one way, so you can't rotate it and plug it in incorrectly. So when I see the key, the little plastic part, I can start counting the pin numbers. This is pin number 8 right here. Pin number 8 has this capacitor across it, going to the chassis. This is the bypass capacitor or the resistor. Now the cathode resistor is probably this guy right here. This big thing, he's hooked up to that pin. So this would be, was it 220? I've still got it on my screen here. Let me just look. It's a R10. R10 is 510 ohms. So the first thing we're going to do is measure that resistor and see if it's still 510. These resistors tend to get hot. See, it's a large resistor here. And so it's a high wattage resistor. It's dissipating a lot of heat. Okay, and think it's supposed to be 510. So because they work hard, they run a little warm, the resistors tend to wear out early. Most resistors, in wearing out, their resistance goes up and up and up. You can burn them right out, but you can also just kind of make them fade away. What do we get? 536. Well, that's not a problem. That's good. It doesn't warrant any attention. So I'll keep this here because we're going to want to make that same measurement, only it's going to be voltage next time. Oh, did I have my tube manual open? No. What is the proper bias on a 6F6? Or what is a typical? That's a better word. Typical bias. 6F EF G 6F6. Here we are. Power pentode. Just double checking. Yeah, cathode is on pin 8. The grid, just for interest's sake, is on pin 5. Try to remember that. Pin 5, pin 8. We want a fixed bias, cathode bias. So this is how the tube is being operated under this technique, fixed or cathode bias. The plate supply, I think, is around 300 volts. So we'll do the 285 line here. Grid number 1. Well, they don't give it. You know why? Because they're just going to give the resistor value, 440. We've got a 510 in there. That's suggesting even higher B plus voltage than the 285. And maybe it was. I'm not remembering it. So it's not going to give a bias voltage unless we look back here. Under fixed bias, you'd be aiming at 16 volts or 20 volts of bias. That's a lot of bias voltage. 20 volts. So we'll measure it and see what we get here with the radio operating. Now, a couple other things. We also want to identify, we're going to look at the schematic here. Flip to the schematic. Okay, so we were just looking at this resistor here. Let me zoom in just a wee bit. So yeah, we were looking at this resistor. This is the 510 measuring, did I get it wrong? 510 measuring at 536 or something like that. This is the bypass capacitor that's sitting there. This is how it's shown on the schematic. This capacitor here is, I think this was the 1000 volt capacitor. I'm not sure now. I'll have to take a look. It's right on the plate output of the output tube, and it's just paralleling, not quite paralleling, it's trying to drain out literally any unwanted harmonics that have developed. So a harmonic, let's say you're feeding a signal through here, a signal you can hear, like a tone, maybe 200, maybe 2 kilohertz. So that would be a whistle. That would be a fairly high-pitched whistle. When it goes through the tubes here, it may be distorted, I guess is the right word, and the result is, along with the original 2000, you get a 4000 and 6000 and an 8000 tone coming out. You don't hear them separately necessarily. It just affects the sound of the original tone. It doesn't sound quite right, or it has a different sound to it. You know that story about tubes and their wonderful tube sound? Yeah. That's a really big debatable thing to talk about, but I know guitar guys and other people just love the sound of tubes. You know, you're not supposed to hear the electronics in the radio or the amplifier. You're not supposed to hear any of it or be aware of it. You should be able to swap one amp for another, for another, for another, and never hear a difference if they're working right. Fat chance on that though, because all these things have limitations, transistors too. So part of the limitation of these tubes is they generate harmonics. Now, so I explained how that's a multiple of the original frequency, if you like. Now, I may have this wrong, but I believe even multiples sound fairly pleasing to our ear, and odd multiples sound kind of harsh. And if I got the story right, and I may not, tubes tend to produce even harmonics, which sound comfortable, whereas transistors, the process is quite different. When you're getting harmonics, it's because you're overloading the transistor, pushing it beyond its VCC voltage, I think. Anyway, the result is you get the third harmonic, and I guess the sixth harmonic or something like that, and it's grating. It sounds grating to the human ear. We don't like it. So, okay, enough of all that. So this capacitor's job is to get rid of those high harmonics, keep them out of the winding here, and for some reason, 1000 volt. I'm not exactly sure why that would be, and maybe I'm wrong. Maybe, well, if we can look, it's be written over here. C18, 600 volt. Because where did I see 1000 volt? Here we are, 1000 volt. C20. Where do you need to put 1000 volt capacitor in a radio like this? C20. Well, we'll keep her C19. We'll have to keep our eyes peeled for C20. 1000 volts on the incoming line? I don't know, lightning? I don't know what they're doing here. 1000 volts, that sounds just nutsy to me. But then I'm not a radio engineer, am I? I'm just a guy who fixes them. So I don't really know everything about all the design things that go through the heads of the design engineers when they're doing this stuff. So I don't pretend to have that kind of knowledge here. Okay, so we should measure the voltage here. See if it's near the bias number that was in the book, minus 17 or 20 volts, somewhere in that range. Then we should measure the voltage on pin 5 against ground and see if it isn't 0. It should be 0. But it could be positive to ground because this capacitor may not be doing its job. So we got to deal with this one too. So one thing at a time. So we'll what we'll do is we'll make the measurement, and then we'll start picking these, basically 2 capacitors, and get rid of them. Okay, that's the plan. That is the plan. Now, can I really identify those capacitors? Well, you know, here's the tube, and here's 2 capacitors sitting right here, and it's very likely those are the 2. Now, one of them is right on the grid connection here. And that'll be the one that's conveying the signal to the grid, I would think. And where's it conveying it from? It appears that the other end of the capacitor is connected. Okay, so it doesn't add up for me. Not adding up for me. This capacitor is connected from the grid of the output tube to not the grid. Okay, Jim, that's the cathode. The grid was number 5. That's this guy over here. Here's the capacitor connected to the grid, and it's coming from the tube here, which is the tube that's supplying the audio. It's a preamp tube supplying the audio to the output tube, going through this capacitor. So this is the guy who, if he's leaky, and look at it. Can you look at it? It's hard to see in there. He's almost certainly leaky. A little bit of a leak can do, I wouldn't want to say damage, but can set things up inappropriately. So we're going to check for that now. As planned, we're going to read the voltage as soon as I remember how to use my voltmeter. We're going to turn the set on now. So that's the first time today. Let me just do a quick check of things and make sure everything looks safe. We're switched on at this point with the volume up just a bit. Okay, and we're in here. We still have the antenna connected, but the antenna is switched off because I was listening to radio last night in my, I don't know what to call it, my other room, my shack, my office. I don't know. Can't settle on it. Shack just doesn't sound right. Office sounds better. I'll have to call it my radio office. Okay, let's get these voltmeter going here. So I want to read from the chassis to the grid. Watching this meter. We're reading plus because I have the red in my hand. Plus. So we're feeding the radio with 86 volts, and we're getting 5 on the grid. Okay, the bias voltage 0. Did I touch the wrong thing? There we are. I don't know why I got to what I got. So 10 volts of bias. Okay, so in the book we saw 17 and 20. We got 10 here. We got 10 here, but we got to take away the 4 from here. So the actual bias is only 6 volts on this tube. That's not good. Let's give it the full voltage here. A little audio. Okay, just a reassurance that there is something going on. Ooh, that sounded like that motorboating again. Okay, full voltage. Although we solved the major part of the motorboating, there could be more feedback circuits that are not being controlled properly by capacitors in here. Okay, so we can hear the speaker, not that it matters. It just reassures me everything's operating. What we want to read is those 2 voltages again. So voltage to the chassis on the grid. Well, surprising to me, it's gone down a bit. I would have thought it would go up and get even more negative, but still, that should be a 0. The reason it's not a 0, the old capacitor is leaking some charge through. Now we'll look at the bias. Pick the right terminal there. So now we're up at 18 volts, which is just fine. That's really quite fine, as long as we can get rid of the 4. So that's the objective. Get rid of the 4. See, if you have the grid and you have the cathode. This is the cathode here. And you got to maintain the grid at a certain negative voltage relative to the cathode. You got to make it go like this. So let's say this is 20 volts now where it's supposed to be. So the way they do this is, instead of pushing down the grid, they push up the cathode with the cathode resistor. And that's why I'm reading at 20 volts on the cathode resistor. But you see, the grid is still negative now compared to the cathode. Except the grid is being pushed up by a leaky capacitor and some charge coming from the tube previous. That's being pushed up. So you end up with this much bias, this gap between my hands here. Instead of this, you're getting this. Not the end of the world. What happens in the 2, it doesn't affect the sound very much until it gets really, until the bias reduces so much that the incoming signal is greater than the bias. The bias is making room for the signal on the grid. The signal on the grid, making room. So if you don't have enough room, the signal on the grid, you want it like this. If you look closely, you'll find fingers inside these tubes wiggling around like that. Okay. You know, maybe it's time for a coffee. So I'm going to do this capacitor here. That's all, and then run the radio again and make those same measurements once again. And what are we at? 112 volts this morning. It's the nuclear plant, so maybe just. Ooh, what happened to the sound? The sound just faded away there. Not that the sound faded away, it changed. Like I still output coming from the. Wow, who knows? So, you know, another possibility here. This could be happening right in front of me, and I'm right in the position to test for it. What happened to the bias on the output tube just now? Did it go off? Did it go off? So this we got 4 here before. Okay, we're still getting around 4. And on the bias we were getting 18. We're still getting 18. So I don't know what made the radio go quiet just now. And that's about all I can say about that. We'll continue with what we're focused on. I mean, there can be a number of problems cooking away in here, causing various effects. And they're all on top of each other, so to speak. So anyway, we'll do it one thing at a time. The next thing is coffee. And I got to slow down my talking. Wow. Okay, let's give this capacitor a test. I have it connected down here already. It's not this one. That one sitting there. This is literally is called a blocking capacitor, and its job is to block voltage. We're going to measure its ability, or qualify its ability to block current. I've got this set to 50 volts. If you're hawk-eyed, you can see it says 25 here, but in fact it puts 50 out on here when I do this test at this setting. So watching the eye now, what to do. Okay, so it's just barely separating down here. You won't be able to, oh, you can see it. You can see it, just barely. So as capacitors go, this is a bad one. Not the worst, but this is not up to the job. This is one position where a leaky capacitor can throw the radio off, and it does it in a way which isn't particularly noticeable. Because I didn't explain this before, if you have the bias not negative enough, then more current flows through the tube all the time. The current flowing through the tube all the time doesn't do anything to the speaker. You don't hear that. It's the changing current that makes a sound in the speaker. So you can have this current flowing through the tube, but there always is some current flowing through the tube, and you're just unaware of it. As an operator or a listener to the radio, you got no idea. That current could be large, it could be small. You can't tell listening to the radio. When the current gets large in the tube, what you're essentially doing is wearing the tube out unnecessarily fast. And these are already operated and designed in such a manner that they wear out during the life of the radio and need to be replaced. You don't want to help that process. An old radio like this, these output tubes are getting rare because they wear out. So output tubes and rectifier tubes are becoming rare. So they are rare. So you don't want to be unnecessarily damaging these tubes. So in the case of the output tube, the thing to check is the grid bias and make sure it's correct. And now, having given the speech, I'm now going to find out if I'm full of crap here. We're going to turn on the radio and repeat the two tests, the two bias tests. One, the cathode bias resistor measurement, and the grid to ground measurement. Okay, I think we're all set here. Away we go. Radio's on. I guess you could see the pilot light come on, so that kind of gives it away. Okay, we're going to go up to full voltage supply, which now is 112. That's just a wee bit low. Just go a little bit higher. Okay, you can hear the radio coming out of the speaker, so we know it's operating. First test is voltage on the grid. It was 4 volts last time. What is it this time? If it's 4 volts again, I'm going to have to explain myself. We're in some trouble here. I think I made a mistake. Well, I saw 56 volts on here. I think I hooked the capacitor up to the wrong terminal down here. So yeah, classic here. I made a mistake. I cut the capacitor out. I did not put a clip lead on the lead I cut it away from. I looked at the radio later and I look at it, you know what? I think it's this terminal because I think I can see a little tidbit of cut wire there. Yeah, that's got to be the one. So I hooked it up there. But you know, that may not be the right one. Wait a minute, wait a minute, wait a minute, wait a minute. Hooking up the capacitor to the wrong terminal shouldn't generate a 56 volt reading there. Reading the wrong terminal would though. Yeah, if I hooked it up to the wrong terminal, I'd then taken the voltmeter reading on the wrong terminal. So over here is the tone control. Here's the tone control capacitor right here. You can see the wire coming across and it ties right to the terminal I put the blocking capacitor on. Let's look at the schematic here because I'm not convinced of anything. I'm not convinced I made a mistake. So if we look here, we see here is the tone capacitor and it's connected right up to where I connected the capacitor. What happened here? How did I measure 56 volts on this? And the radio was working. If you push the bias too far, the tube will stop operating. You won't hear anything coming out in the speaker. How do you get this to happen? So you see there's supposed to be 60 volts here, and there probably was around 60 volts there, and it showed up on this side. Or am I just turned around? Did I get turned around? No, I'm not turned around. In other words, I'm measuring the wrong side of the capacitor. Did I measure the wrong side of the capacitor? What happened? I'm getting squeaky. So I know what's necessary now. Stop, drink some coffee, and come back in here and figure out what happened. Okay, so reading 56 volts there, I don't think it's really possible. I think I made a mistake. I must have made a mistake. I must have read the wrong terminal or something like that, because I don't know how you can get the voltage there, and a capacitor is not going to pass 56 volts unless it's shorted. Oh my gosh, it can't be shorted. It's brand new. It's brand new. No, not shorted, or we would see that. No, it can't be shorted. That's crazy. So I'm going to repeat it. I'm going to repeat this. The thing was, the radio was operating. Everything seemed normal. I got a funny test result. Maybe I read the meter wrong. Maybe it said 5.6. I'm very anxious to see a 0 on there, by the way. Okay, so here we go again. Here we go. We're on the DC. 60 volts. Expecting a 0 to show up. Okay, I'm grounding one lead to the chassis. This capacitor is definitely connected in the right place. What do you see there? Well, that looks like a 0 to me. Did I touch this one? Maybe that's what happened. Maybe I touched this terminal here. .200 volts right beside it. Maybe, well, I didn't hold it all long enough. Maybe if I held it longer, it would have said 200 volts on there. And then so this is the bias on the grid now. It's a 0. Okay, we're going to give the radio the full. We're going to plug it right into the Bruce nuclear power plant. We got the Darlington nuclear power plant, the Bruce nuclear power plant, and the Pickering nuclear power plant. The Pickering nuclear power plant was built in the late 60s, early 70s. It's among the biggest nuclear power plants and oldest nuclear power plants in the world. Now here's a little, I'm going to make a point here. Everyone's worried about what are you going to do with the waste that comes out of a nuclear power plant. We got to bury it, 50,000 feet down in the ground or something. We got to do something with it. What do we got to do with it? What are we even doing with it? What has the world been doing with radioactive waste coming out of nuclear power plants? What has Canada been doing? I can talk about that. So all the nuclear waste that's come out of that plant, there's 8 reactors there, and they've been running since the early 70s. most of them. So they've produced probably more nuclear waste at that plant than anywhere else in the world, or certainly, what'd they do with it all? Well, it's just stored in the back, behind the plant. They have a storage facility, and they store it there in these special containers. They're up off the ground. They're not on the ground. They're up off the ground. And they just, including, would you believe it, in that case of that particular power station, nuclear power plant, they replaced all the tubes in the first 4 reactors because they were found to be deficient. They cracked because of some radiation thing that they didn't anticipate. They had to replace all those tubes are behind there, are behind the plant. All of it is stored behind the plant. What's the problem? There's no problem. There's no problem. The highly radioactive waste is kept in a pool until it calms down enough that they can then put it into steel containers and stuff like that and stick it in the back of the plant and keep people away from it. Is there some reason we can't do that for the next 50 years? We've been doing it for the last 50. No. There's no concern here. That's my opinion, but I have an opinion about opinions. My opinion about opinions is we should all keep them to ourselves. We should not share opinions. Well, okay, maybe if I'm an expert, I can lend my expertise or quote opinion. Yeah, okay, fine. Go to the doctor, listen. Yeah. I'm talking about ordinary people talking about stuff they don't know anything about. What we should share, and we do that all the time, don't we? What we should share are the facts upon which we base our opinions. You know, opinions are a dime a dozen. I'll bet you've got some. I'll bet you've got some right now. I'll bet you if I took you out front somewhere and pointed at a tree and said, if you're going to cut that tree down, which way would you do it? And you probably have an opinion about that. If I push you, you'll come up with an opinion. You should cut it on the left side. I mean, you can get an opinion about anything. Opinions are dirt cheap. We have them by the millions. They're worthless. Don't share them. Share the facts. Facts are hard to get. Facts are expensive. You have to spend time and effort to get them. Share those things. They're of some value. Let the other guy make up his own opinion. Don't worry about it so much. That's my opinion. Oh man, I get so speechy in here sometimes. What is the matter with me? There's nobody here to stop me. That's the problem. Okay, focusing back on the radio again. Calming myself down. Let's measure the bias as supplied by the cathode resistor. Okay, we're on the 60 volt scale there. The cathode resistor is working on this. Look at that, 18. Well, you couldn't ask for a nicer number, because that's right between 17 and 20. And once again, going back to the grid, 0. Beautiful. A job well done. So there we are. So now the output tube is running just as it was, but with less current flowing through it. Its input mouth, if you like, is open wider now. So if you turn the volume up, a bigger signal can fit in it without smashing up the radio. Okay, where are we on the clock? I think that's going to be it for today. Just one capacitor? No, I got to do another one. Okay, well, let's do another one. So there's another one right down in behind here. What's it doing there? It's hooked up to the output tube, and then hooked up, what looks like it's hooked up to the field coil, because it goes to the plug here. Capacitor related to the output tube and the field coil. Let us take a look at the schematic here. Okay, so here is the field coil, and we are looking for a capacitor. Oh my god, it could be anywhere. It could be anywhere in the radio. Could be anywhere on the schematic. Field coil. Oh, I don't know where it's going to be. We're not going to be able to locate it. Is it the field coil it's hooked up to? Or could it be on the primary? So not the field coil. This is the electromagnet here. But this is the actual sound going through here. And the capacitor appears to be right across from cathode to plate. So I have a capacitor between the cathode and the plate. C18, and C18, and the value is C18. value is hard to see here. 006, I would say, 600 volt capacitor. Now, most of these capacitors are 400 and 200 volt ratings. This one's got a 600. And then we got the wild guy over here at 1000. So 600 volts, eh? Most of my capacitors that I install are rated for 630 volts. So okay, 0.00 something. This is the harmonic killer. Okay, that's got to be the one we're looking at. Tied to the cathode. Can it be tied to the cathode in a roundabout way? Like it comes down to the field coil plug. The cathode does not present itself on the field coil plug. The cathode is over here. So what is that capacitor doing there? It's going from, we do this by pin numbers, pins, from the cathode. So I can definitely see this connection right here. And the other connection, unless I'm misinterpreting it, or maybe they've done the spare terminal thing. No, that's it. So I'll show you what I'm talking about here. What's he talking about? So I like to identify these capacitors, and I don't like to do it in a way that's, there's more than one proof for something. So I feel reassured that I've got it right. So we are looking at this capacitor here. You can see the connection here. This is the grid connection. No, it isn't. This is the grid connection. This is the output plate connection. Oh my God, I'm all confused. I didn't drink enough coffee. This is the cathode. This is the cathode resistor. This is the cathode bypass capacitor. This is another capacitor attached to the cathode. This capacitor is tied to one wire on this guy here. So there's a red wire coming from here. So it's as if it's connected. Yeah, it's as if it's connected here. That would be, and I measured the B plus on this. This is the grid. I measured B plus here. So there we are. So they could run the capacitor from here to here, but instead they run it from here down to there just because of the physical size of the capacitor and the need to make a connection to a terminal in some comfortable way. I could put a smaller capacitor right across here, like physically smaller capacitor across here. It'd be done. That's great. That's great. Now, this capacitor, which I'm about to cut out, Jim. What a bad boy. Bad boy. The radio's on. Crying out loud. Sticking my fingers in there and everything. I have to go punish myself now. No coffee for you. I must be punished for that. Okay, for my punishment, I went out in the garage and cleaned things up for a little bit. So that's a really serious mistake in my mind. That's something I do not want to do. Forget that the device is on. There's a number of visual clues I have here that remind me constantly that something is turned on. Visual clues, and the most important one, sound coming out of the speaker. Why sound's coming out of the speaker, I won't forget that something's on. If the pilot light is in view and I see it, I'll know, and just in the back of my mind I'll remember. If by some chance I can see the vacuum tubes, sometimes the glow is visible. That's another thing that just keep reminding you that the switch is on. The best one is the sound coming out of the speaker. So in this case, the speaker was silent. I couldn't see the light from where I was standing. It looked like this, what I'm seeing. from where I'm standing. And somehow I just totally forgot I had the unit on. Whew. Yeah, so danger to me? Probably not the greatest danger because, well, there's a couple ways of looking at this. One is this guy's plugged into an isolation transformer. But the moment I connect a piece of equipment in my shop to it and put a ground on the chassis, it's as good as being plugged right in an outlet at that point. So under some circumstances, very hard to get a shock off this thing. I could take my finger and touch anything at all while it's operating, probably not get a shock. Other circumstances, not the case. And just as something else I try to do, I think if you're an electrical person, you're probably trying to do this too. You try to keep your spare hand, out of the way. You literally, stick it in your back pocket or something like that. I try to remember where my left hand is. I try to make sure I'm never grounded to anything. Or if I am grounded, I'm aware of it. Like if I'm touching something that's grounded. I try not to touch two different things. My whole life now I'm like this. I really feel uncomfortable if I'm vacuuming and I touch the sink. Yeah. And you're probably the same if you've been doing this stuff long enough. Doesn't take too many shocks to smarten you up. That's for sure. Okay, so what am I doing now? What am I doing? I was in the middle of examining this capacitor. Now, see, this is also why I normally pull the plug out also, because there's no doubt now. There can be no doubt. I cannot accidentally energize it, by throwing a switch by accident. The plug is out. Okay. Okay. I think I'm ready now. So we're going to nip out that capacitor, and then we're going to put a replacement just across here. So let's nip it here. Now, in some cases, you do not want to relocate components. Not that they're in some very special place. They're just in a place where the radio has been, designed, developed, in the laboratory before being manufactured, and everything needs to be in the same place for everything to work the same way. So if you do relocate a component, especially if you transfer, let's say, the ground point, like what I'm doing right now, I'm going to kind of move the capacitor this way. You need to be cautious. Down here in the audio part, not so much of a concern, but in the RF part, you could set up a situation accidentally which creates an oscillation, and you might be really confused by it because you didn't really think you did anything that could cause something to go awry. But just relocating a component, it's still electrically wired properly, but just in a different spot in the RF side. Unintended consequences, I think, is you can imagine in a factory environment, they want each one of these radios coming out looking exactly the same. Okay, we're ready. 50 volts, watching the eye. Wow, did you see that thing pop open? 150. Can't quite do it at 150. In fact, I've never seen this before. It's closing. It opened up a slight bit and it's closed back. Can't say I've ever seen that before. 0.006, just like on the schematic. 1000 volts. I've got the 1000 volt capacitor in my hand here. 1000 volts, hey? Really? Well, let's keep pounding it. That's 250 volts. Nah, I'm not going to do that. Once the eye's not opening, there's no more to be gained. I don't think I have a 1000 volt one, but didn't it say 600 on the... I think it said 600 on the... It's definitely 1000 there. Okay, 0.006. Put it in there. Test the radio again and see if I get electrocuted. Well, to my surprise, I pull out the capacitor out of my tray. It's a little bigger, 0.008 instead of 0.006. But look, it's a 1000 volt capacitor. Should I put it in? It's a little bigger. That's debatable here. 0.06, 006 and 0.008, that's a difference. My other capacitors are 600 volt capacitors, which are probably going to do just fine also. This is a 004, 6, and 8 are in here. 006. Let's check this out. I should check out that other one too, just in case. Modern capacitors are actually quite accurate. So this says it's 6,700 picofarads, which is a 0.0067, and this thing is rated 6.8. So it's just right on the money. 0.0068. So I could put this in. Let's just try the 1,000 volter. So this one says 8,500 picofarad with 0.0085, and it's supposed to be 0.0082. I don't think we should put in a bigger one because this location could affect the tone in the radio. It could muffle it. If we put too big a capacitor there, it could muffle it, I believe. So we don't want to do that. So we're going to put one right across there. No, wrong plug. Okay, so I am going to fish this capacitor in here. It's going to look like that when I'm done. Okay. Oh, heavens, what are you looking at? Up here. Okay, I was just saying I'm going to put this capacitor in. Oh, a dummy, you know, I took off the clip lead and then looked away. So, yeah. I'll put it in the right spot, I'm sure. Okay, that's good. Got the capacitor installed here. And the other one over here. Okay, now we're going to operate the radio again. Not very likely I've made a mistake, but let's do that. In fact, maybe I'll go throw the antenna on and we'll just hear a station or two come out of it. So there still is one more capacitor sitting in the audio circuits, and that's this capacitor here, and its job, this one back here, is to enable the tone control. Not very important. I'm just going to leave it for now. And probably towards the end of the capacitor process, I'll probably end up replacing both of these and this guy too. But we're not there just yet. Let's operate the radio. So we're plugged in, switch is on, volume is down, power is going on, power is on. What band are we on here? Okay, we're on the broadcast band. We're going to give it the full treatment. Well, I just cut in another nuclear generator when I hit the switch here. Okay, there we are, and we're tuning. We're tuning. Not much. What happened? Wasn't this picking up stuff before? No. Well, that's kind of weird. What happened? Phono. Not that, this. You can still hear that buzz, eh? Even when it's on phono. Where are you, radio signals? Let's go on the shortwave. Oh, that's where you are. That's what we can do. We can try cleaning this switch up. Yeah, okay, switch off. That's a good idea. So we're going to hit that switch with this expensive stuff here. Deoxit. Try Deoxit. I'm not promoting this product, okay? I'm just talking about it. Provides flushing action. Provides quick dry. No solvents. All electronic connections deteriorate, causing reduced performance and eventually total failure. Deoxit rejuvenates and improves performance and reliability of all, they put all in capitals here, of all electronic parts and equipment. Just start hosing it. Hose her down. Directions. Turn off the equipment. Adjust the valve all the way down or up until it clicks into place. That's this thing here. Yeah. Note. Test for compatibility before use on delicate devices. Phones, cameras. You're going to spray this stuff on your camera. It contains no solvents. On delicate devices, spray onto a swab or a cloth, then wipe on metal surface. Do not spray directly onto device. Unlimited uses. Really? All metal electronic connections. Audio, video, computers, cables, rechargeable devices, flashlights, everything they could think of. They, get right down here. And many, many more. So I don't think there's anything really spectacular about this stuff. I really don't know what it is. What does it say what it is? It says it's not a, oddly enough, removes oxidation, improves connection, seals and protects surfaces. What's it? Just a pile of malarkey. That's what I think. Okay, we're going to shoot it in there, though. I'm going to shoot it right in here. Shoot. She shot a lot in there. I'm going to work the switch. Sometimes when you do this, you start out, the switch feels smooth. And as you do this and the surfaces get cleaned off, it becomes less smooth, more gritty. A gritty feel. Let's spray a little bit more in here. Whoop. Now, I often use WD-40 in these kinds of situations. Made by the same company. I believe it's made by the same company. Craig Laboratories. Craig Laboratories. Some WD-40 here. Where's this coming from? The WD-40 Company of Canada. Maybe it's not made by the same people. WD-40 makes a whole line of products that are like this. I thought this was it. This is coming from somebody else. Okay, so we've done this. I've oiled up my fingers. We're going to operate the radio again. Where's the cloth? Okay, let's try it again. Volume down. Are we safe? We are safe. Dim bulbs, okay. We're all okay. Everybody's okay. Oh, this is greased up here. Made in the USA. What is happening there? Some weird going on. Those sounds are, it's nothing, it sound mechanical, they sound like I'm banging on something. That's the speaker making that sound. The clicking, it's coming out of the speaker. Hey, you're still not producing anything here. Behavior of the switch is consistent now. Weird stuff. Oh, there it goes again. Wow, I don't. It sounds like it's not too good for the speaker. Well, I've really wrecked this radio up at this point. I wouldn't be too concerned. Let's try the sensitivity test again like I did last time, which I touched the tops of these things. Let's turn this down. So it's coming right through the radio, so the radio's operating. Did I not put the antenna on correct? Yeah. It is the antenna, isn't it? Yeah. Well, not going to worry too much about it, because we heard the radio work in the past. Whew. It just sounds like I've got a broomstick and I'm banging it on something, but it's coming out of the speaker. Ooh, 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 ooh. The swooshy sound, I think, is, and I'm just taking a wild guess here, it's related to the mixer mixing up a bunch of signals that we just assume not have it mix up. And that's a stupid statement, but I'm going with it. That heterodyne toning in there. Okay, that's enough of that. We're not going to get any further with that. So the thing to do is continue on with the capacitor replacement. There's only two left. Two left, and then they could do the tone one at the same time. 2 more capacitors. We'll do it tomorrow. Hopefully the radio will be working after that. I'll make it work. And we'll keep going. So thanks a lot for watching. Step by step, we are improving the radio, even though it doesn't look like it. See ya.